Hello, boys and girls. It's been a while, but I just had some fun with some light Python scripting and some basic geometry and thought, hey, why not sit down and make a short clip about my findings, let's say. So for some context, I have been reading into a project I found 2 weeks ago. There's pretty how do I say, special or unique kind of paper with a very like modern math approach to blockchain and consensus stuff that I have been busy in the last year. And since this kind of tries to marry two topics I fancy, I'll read into that on the weekend and maybe make some more videos about that. So in any case, this is written actually in the context of a project called Constellation, or DAG. That's the name of the token. DAG stands for Directed Acyclic Graph, and this the company or lab or project or community has a logo which ironically is the polar opposite of directed acyclic graph. So this is a graph which is not directed and has certain a lot of holes, and but it looks fancy, and I was looking at that and thinking, how to capture actually the structure, what are the properties. And so I started to toy around with pen and paper, and then took out the Network X Python library that I had been using for my wiki math foundations hierarchy project, and was trying to script together this logo, and this is what I'm going to do now. So let's analyze this logo a little bit. The perspective I'm going to take here in this video is the following. So there are hexagrams. The outer one is obvious right here. You can look at a hexagon as two triangles. If you connect then the outer, if you dig the convex hull of that, then you get the hexagon. And this is what you see in the logo. And apart from the outer one, there are also several inner hexagons. So this is the outer one. Let's say from the center to this outer point here, we have a radius of 1. Then there is an inner hexagon with a smaller radius, like the radius is going from the center, not to this point, but actually to this slightly tilted point, right? So if this is a sharp corner, then this is the sharp corner of the inner hexagon. This is tilted by some angle. And then there's some radius going from the center point to this point. And then, do you have this kind of aperture made from the outer and the inner one, and you have these nice triangles there. You can see that these lines connecting one node to the point to the node that comes to after, if you connect them, then this gives the edge of the inner hexagon, right? And once you got that, once you have the construction, once you know how to map from the outer one to the inner one, once you know the transformation, which is comprised of a slight tilt, a slight angle rotation, and a slight scaling to the inside, then you can construct the whole thing, because the next hexagon is obtained by the same process from the first, like from the first to the second, from the second to the third, and then there's another fourth one. I think throughout this video I will call these hexagons also rings, because they are like closed, and then you, apart from the rings, you have the connections that connect two rings, right? From every point you have basically two edges. One is going to the next point on the ring, and then there's one going to the corresponding point on the next hexagon. And this happens from the first to the second, from the second to the third, and from the third to the fourth, and then it stops, of course, right? So you have 4 times 6 nodes, so 24 nodes, and then you have 7 times 6 edges. It's only 7 because in the last one, you know, you don't go deeper. I mean, you could obviously, you know, take this to infinity and go deeper and deeper, but the logo stops there. Okay, so the question arises: what is the angle that takes you from there to there, and what is the scaling factor? And if you look at the Wikipedia page for the hexagram, and scroll down a little bit from this picture, actually, it kind of becomes obvious that there's this nice symmetry. Like, right, if you take the hexagon here, and if you connect these lines, then you see, oh, there are these small triangles, and this in a hexagon obviously makes up for 6 more triangles, if you will. So you can go from the upper point to the lower point in 4 steps. 1, 2, 3, 4. So this is on the middle line, and the question arises: okay, from the center to this point, if this is 1, this is 1/2, then this is a little bit more than 1/2, right? This is going to be 0.5 or 6 or something in between. So far so good. Now if we look at the hexagon article, then if you scroll down, there's not only this nice animation where they show you how to create the hexagon with compass and straight edge, but right beneath that I found this drawing, and so there's exactly the information that we want, right? So in our logo, we said that from the center to the outer corner, right, there was 1. Then here we go 1/2, so R is 1/2 of 1, right? So actually they have some letters here too. So the center to the outer sharp corner it would be D. The 1/2 of D would be R, and then what is capital R? Well, it says here. So the relation between the small r and the capital R is square root of 3 divided by 2, and you get the square root of 3 if you just do the Pythagoras, because if you look at the logo, then you have, you know, these very nice triangles, and then, you know, if you do the school math, then you get there. So if D is 1 and there's 1/2 and there's square root of 3 divided by 2, we can cancel out the 2. So we know that R is actually D, or 1, divided by square root of 3, and then that's actually the thing that we wanted. So 1 over square root of 3 is the magic number, and you can plug it in and you know, to whatever calculator, and you find out that 1 over square root of 3 is actually, I don't know, 0.577 something. So this is the, you know, if the half line here is 1/2, then the difference from here to here is obviously a little bit smaller than here to here. And by how much is it smaller? Well, it's just, you know, 0.7 something. 0.07 something. Okay, so we got it more or less figured out. The only question that's left is what is the tilting angle, and that's also very easy, actually, because take the outer hexagon, tilt it once and you get this one, tilt it twice and you get the inner one, and the inner one, if you notice, is not actually tilted anymore with respect to the outer one. So there's a rotation that if you do it twice, you get back, you get the symmetry. And obviously the hexagon has a very magic number, namely number 6, right? That's what the hex stands for. So you have 1, 2, 3, 4, 5, 6 nodes that make up for the hexagram also. And so if this whole circle is, the circumference of circle, 2 pi, then the rotation from here to here is 2 pi over 6 or pi over 3. And the rotation that we seek is the one which rotates something in between. So this is actually 2 pi over 12. So 2 pi over 12 is the other magic number. The first one being 1 over square root of 3. The second one being 2 pi over 12 or pi over 6. Yeah, okay, so we got that figured out. I think we got all. Yeah, so one more thing. We're going to use, since, I expressed the whole problem in terms of radius and an angle, we're going to use polar coordinates, which is the parameterization of points using exactly these two values. And for that, we gotta know that since the graph library from Python that I'm going to use takes to draw stuff in its easiest forms, wants to have Cartesian coordinates, we got to know this formula, right? How to map from angle and radius to x and y coordinates. So we're going to need a cosine and sine, and also by standard conventions, you got to have the x-axis usually, horizontal, and so you would start here. So this is the 0 angle, and the constellation logo just happens to have the sharp edge, the sharp corner here. Not on this side, not on the math 0 point, but actually on after 90 degrees. So you could say that the outer circle where we're going to start is actually already tilted, as far as at least sine and cosine goes. So that's my last remark. Okay, so much for that. I have here my terminal, and we are going to, I will actually not even write a script. I will do everything in the interactive environment. Firstly, we're going to need some modules. So from the math library, we're going to import square root, cosine, sine, and pi. And I forgot import. And now we can actually check, what is 1 over the square root of 3. And that's this number. And then import, we're going to plot it, of course, because otherwise it would be super boring if we just show you the code. So we need the matplotlib, the mathematical plotting library, I suppose, and pyplot from that. And that's usually imported as plt. And it takes a while because my computer is super slow. And once we got that, we import the network X library as nx, network X. And this is one of the many graphing libraries that I've used it before. So that's why I choose it. What we're going to do is more or less basic. So any graph library would probably do. And if you have time, then I'm going to also have some fun with random deviations of the logo. And for that, we're going to import the uniform distribution and import it as dw. Import. So, okay, so we're going to create a graph. I call it capital G as its standard, and for this I call this constructor, and then we're going to set up once and for all our special numbers, which are 2 times pi divided by 12 and the special radius 1 over square root of 3. So and now, okay, so we have, as I said, 24 indices, right? And since I'm going to you know, I could just you know, find out how the edges are connected and use the graphing library to print out the graph, but then it will be all, you know, it will put the nodes where it wants to. So we're not just looking at a graph, we're also looking at a graph where we specify where in the Cartesian plane the nodes are supposed to be. If you look at just graph array, then it doesn't care for the position of the nodes, but if you want to have a nice picture, then you do. So for that sake, I will use the index on each of the 4 rings, right? And I will I will denote this index on the ring by k, and I will denote the index for the ring by n. And I will now write a function that gives me an index for a distinct index for each node, and a parameterized by the index on the ring and for the ring. So basically, I write a function which takes 2 indices and gives me another one, and this is going to be the index of the node. I call the function I for index and return. What's this going to be? Well, there n is going to range from 0 to 3 or 1 to 4, right? I mean, Python starts at 0, so this is going to go from 0 for 3. And on each ring, we're going to have 6 nodes, and we're going to have them unique, we add k. And so now if we range from n from 0 to 3 and k from 0 to 5, we're going with I from 0 to 23, which are our 24 nodes. So far so good. And now I'm going to define the phase of rotation, right? The argument to the sine and cosine. I call the phase f. I give it an overall phase, which I call p, which will vary, and I will use to, you know, rotate the whole ring. And since we can distinguish the nodes by their index on the ring, I also pass k. So, and this will return 2 times our fundamental phase rotation of p0. So since there are 6 nodes on a ring and they are apart by 2 pi divided by 6, right? 1/6 of the circle, we need 2 times our fundamental rotation of 2 pi divided by 12. Okay. You have probably seen it, but I only notice it now. I have to do divided by 12, not by 2. So okay, good that I catch that now and not after I defined all functions in terms of this wrong parameter. So what we're going to do? K return. Okay, so 2 times p0 times. Okay, this is the 1/6 of the whole circle. Then for each point we do that, plus then an overall phase, and plus, and then that's what I mentioned before, right? I give it a head start since the outer one is already rotated as far as math goes. I wrote all of them by pi 0 as well. Let me check if I didn't do another error. No, that looks good. Okay. Okay, and so we also need a map from polar coordinates to Cartesian coordinates. So return. And how do we do that? Well, this is exactly the formula we saw on the Wikipedia page. So the radius times cosine of the phase, and then r times the sine of the same thing. pk. Okay. And now we're going to make the position. So the decisions are going to be a dictionary, pos for positions. The dictionary is one where on the left hand side we have an index. So this is going to be I, N, K, and I will range over all, like I do a for loop over all N and K. And now the coordinates, which are from polar. And now, you know, for all rings, we have different radiuses, radii, which is either 1 or 1 over square root of 3, or 1 over square root of 1 over square root of 3 times 1 over square root of 3, or if we go even to the last level, like 1 over square root of 3 to the power of 3. So the radius that we pass to from polar will be r0, the default, to the power of n, right? So on the most outer one, when n is 0, this will be 1, and in the second one, this will be r0, and if we go deeper, we multiply it again by this factor. Okay, and then we rotate each ring respectively to the next one by another p0. So what we do here is multiply this by n times p0. Only when n is uneven will this rotation be, you know, something else than the identity rotation, where nothing's rotated. And then the k parameter sticks, and we do this for all n in range 4, as well as for all k in range 6. Okay, let's check. Looks good. No, it doesn't look good. From polar, what are you complaining about? Oh, so this is the library dictionary. I need to say separate the index and the value by colon. Okay. Yeah, and now we go to our graph and we add the edges. This goes by the method add edges from, and we pass here a list of edges, and the edges are each given as a tuple of indices. And so, okay, so let's go back to this picture. What I'm going to do is the following. I will do this in 3 different steps. So, okay, let's say this is the 0th index, right? The 0th must be connected to the first to the second to the third to the fourth to the fifth. And the 5th must be connected to the 0th, right? So there's a jump of 6 down, actually, you know, 1, 1, 1, 1 up, and then down. And once we're at the 6th, this needs to be connected to the right node on the ring 1 level down, right? So either this one or this one. It doesn't actually matter, because if we add this edge, then we can connect it to either this or this. But since I have to play around with the indices to make this right anyway, I'm going to do this in different steps. So I'm first going to add the consecutive ones. I leave out the jump, but do this for all 4 rings. Then I will add this the one I left out, and then I will do the connection line from each point to the corresponding node on 1 level down, right? So I connect this to this, but not, for example, there's no connection, no direct connection between a ring and 1, 2 down or 3 down or so on. Okay. So I need the list of edges, which I said is a tuple of indices, and so this is I and K again. Makes sense. And then I and K again, but once more, right? This is the one which comes after the index I was just looking at. And this goes for all K in range 6. There's something wrong. This is not so. And for all n in range 4, but as I said, you know, I want to leave out all jumps. So I say here, do that if it's not the case that the index that you have +1. So if you know, if you're at 5, you don't want to connect to 6 just yet. So if you have 6, and we check that by saying the index modulo 6, if this is 0, like if every 6th one basically, if this is 0, then don't add this edge. Okay, so let me check if that's right what I did here. Okay, looks good. Okay, let's try. Yes. Okay, so I added these edges, and now let's draw this. So I call the network X edges. I draw the graph as far as it is now with the positions that we created, and then I have to pass it a width, and I think 3 works, and then edge color. And so I don't know, this logo is kind of has a nice navy blue, and I could have used the tool to figure out what exactly it is. Well, I would just go with the Python blue right now. B for blue. Okay, so that looks good. Yes, okay. And now I'm going to plot it. So I tried this before once, and I need to set the aspect ratio to equal, otherwise it doesn't look good. So just copied that from the tutorial. Equal, and then there's another argument. It's midnight here already, so I'm a little bit tired. Sorry. Okay, looks good. And now let's see what we got. Show me what you got. Yay. So that's how far we are, right? So we have all the nodes. We have for all nodes the positions, and we connected them in a circle, except we skipped the last parts, right? So that looks good. So far so good. Let me see, we are at, oh my god, we're at half an hour already. Sorry for that. So let's go on. We add more edges. And now I need the connecting lines, right? So to close the circle. So this is going to be IN from this is basically from 5 to 0 and from 11 to 6 and so on. So I can write it like this, right? From 5 to 0. That's that. I mean, you know, it's not a direct graph, so it doesn't matter which I could do first. I could also write 5, 0. And since I have like the point of doing the parameterization of the index is that I now can just do that for all n in range 4, and it will automatically choose the right one for each ring, right? Okay, and now I have to do I think I have to do you know, I didn't try this before. I think I have to call the drawing again. And I think I have to call the aspect ratio thing again as well. Show me what you got. Yay! Looks good. So that's what we want. So we now just added this line and this line and this line, right? Okay. And finally, we do add the connecting lines. So that's add edges from and another list. And I thought about this for a moment. This is, so we take, you know, let's take a look here to explain this. So actually these lines, they start at all nodes. So each node not only connects to the second, so the next one on the ring, but also to one on the next ring, right? The inner ring, one inner ring. Except it doesn't happen once you're on the lowest ring. So this happens on 0, 1, and 2. So I of n and k connecting to one on the next ring, so n plus 1, and we connect it to the corresponding one, which is k. We do that for k in range 6, so for all points on the ring, but for n in range 3 only, you know, because it doesn't go on from the last one. And I think that's it. That looks good. And we're going to draw this again. Yes. And we're going to do this again, and we're going to, let's see. Yay, and here we go. This is the constellation logo. Now we have constructed it. So what we just added was just, you know, this is the 0th one on the ring, and this is, I think, the 0th one on the next ring, and so on and so forth, right? This is the 0th one of the next ring. And that's how it's constructed. So now, you know, we got the whole spiel, and, you know, I did this interactively, but, you know, you can wrap this whole image in a class, in a class, and maybe make a setter for the positions, and make an actor out of it, and then do an animation, right? You can move the points, and you can move the center point. You can parameterize all positions. Like, you can make a setter function which rotates maybe the whole thing. So you can make everything dynamic, and you can make it move, and you can have two, and you can marry them together, and so on and so forth. So I was thinking about doing one more thing here with that. What I want is to you know, make it more colorful and move it around a little bit. So I imported the random module, I think, already. So I'm going to define a function, rand, that takes a point and returns like one of the nodes, the position of one of the nodes, and returns another position, which is going to be project out the first component of the position, and add now this, what I called dw. This is a random number out of a uniform distribution in some interval, and I take the interval 0.1. So since I assumed that the default radius of the outer ring is 1, this is a kind of a value that's, it will be visible, but it will not too crazy, right? So and then the same with the second component, plus the w, and wait a minute, I have to pass it also the lower bound, so 0.1. That's good. And now I will overwrite the positions. When I take the old positions, I will range over all indices in the old positions, and I randomize all points. So I call this rand function that I just wrote on all of the points, which will move them. You know, every point will now get a random value in the positive quadrant. So all points might move a little bit to the right, and might move a little bit up. So for IP, this is the syntax for comprehension in a dictionary. So I is the index of the previous post dictionary, and P is the position, which was the value. And then I have to say dot item. You don't have to do that in Python 3, by the way, but I think I'm using Python 2, I'm not sure. Okay. No, actually, what? Oh, it's items. So let's see how random that looks. It looks sort of random, but I couldn't tell because I was using square root of 3 and stuff, right? So okay, I hope that worked. And I will do the drawing a little bit different this time. So I will call again draw network X edges, G the new positions, and I take, well, let's go for another width, right? Let's go for width equals 5. And now the edge color, I will give each edge their own unique color. So you know what you do here, what you can do is, if you give it a list of a bunch of numbers, and here I give it the numbers 0 to the number of edges there are, then everybody gets assigned some rainbow color. Okay, no. What did I do wrong? Oh, 7 times. As I argued, right? It's 4 plus 3 times 6 edges, right? You have on each ring 6 edges, and then you have 4 rings, and then you have for each node, except for the ones on the most inner ring, another 6 connecting to the next one. So that should also work, yes. And yeah, and finally we call this stuff again, and then so this is like the mutilated version of the logo. Okay, so I hope you enjoyed that. I hope I teased a little bit how actually pretty straightforward the network X graphing module is, right? So this can actually do a lot of things. So now that I have created my graph, I could ask the you know, all the default you know, all the basic graph algorithms I actually implemented, you know, at least a lot of them. So I could ask for a lot of properties of this graph, right? I could ask for, you know, how many I don't know what it has, but maybe some Hamiltonian cycles or whatever properties this graph might have. I could now like let the algorithms talk to me and tell me more about this thing, right? I wonder how it was cooked up in the first place, but so okay, so there we go. I hope you enjoyed this, and you know, it's Friday night. I will tomorrow take a coffee and read into the blockchain commodity thing, and looking very much forward to that. And if I can distill something approachable, because you know it will probably be a paper which requires a bunch of background. But if it's okay, then I'll come back to you with that. Take care and good night.